Hey there guys, so in this video we're going to be learning about the Krushkals minimum spanning tree algorithm, so let's get to it. So what's a minimum spanning tree? It's also known as, let me just do that, okay, it's also known as an MST, so let's take a look at what it is. So for a connected graph, a spanning tree of that graph is a subgraph that is a tree which connects all the vertices together. For example, if we have, let me just draw a quick graph here, okay, this is 1, 2, 3, 4. Can you guess what's the MST for this? We can do basically a simple graph like this. We can have another graph like this. Can you say which is correct? Do you know what is correct? What is not a spanning tree? And what is a spanning tree in this example? I consider 2 here. So what's an MST? Both are connecting all the points, but what actually is it? It's not this and it's this, because it actually connects all the points together. We don't need these 2 diagonals actually. So you can get that by minimum spanning tree. So an MS tree for a minimum weighted spanning tree is weighted and connected, and undirected graph is a spanning tree with a weight less or equal to the weight of every other spanning tree. So the weight of the spanning tree is the sum of the weights of a given edge of the spanning tree. So the weight of a spanning tree, if you have a spanning tree for example, is basically the sum of the weights. Here you can see the sum of the weights given for each edge. So each edge carries a weight. So if edge from 1 to 2 basically carry some 4, then the edge weight basically is 4. Since this is the edge, we have edge weight of 4. So W is equal to 4 in this case. Next, how many edges does a minimum spanning tree have? Well, it basically has v minus 1 edges. Since consider y, let's consider this. If we have 3, how many edges are going to be there? 2. So v is equal to 3, and edge is equal to v minus 1, and that is 2. If we have 2 vertices, then v is equal to 2, and e is equal to v minus 1, that is 2 minus 1, that is 1. Why? Because we only have one edge. So this is v, this is v, this is v, this is edge, v, and v. So you got it. So what are the applications? Let's look at the few applications here which we have. So they're used for sorting the edges in a non-decreasing order of the weights. So edges E1 to En, where this is the highest weight, this is the lowest weight in this case. Looking at weights here. Okay, so we're going to pick the small edge here and check if it forms a cycle of the spanning tree. So if a cycle is not formed, we're going to include this edge, or we're going to actually discard this. So we want to make sure that a cycle is formed, or we're not going to be considering it at all. So we're going to repeat step 2 to make sure that we get a cycle for v minus 1 edges. So the step 2 uses the union find algorithm to detect the cycle. So you can see the union find algorithm here. So we recommend actually you go through the union find algorithm. If you're not, don't worry, I'm going to keep a link in the video below. Just go and check it out so you know what you're doing. So this algorithm is the first algorithm in the greedy set. So if we talked about the first greedy algorithm, and then we already discussed rep frames. So we're finally at Krushkals here. So the greedy choice is to pick the smallest weight, which does not cause a cycle in the MST constructor so far. So let's consider this. Let's consider a following graph here. So we have this graph. So we start at 0. So what's the lowest weight here? Is it 4 or is it 8? Yes, you guessed correctly. It is 4. So we would go to 1, obviously. So let's look at the next weight. Would we go to 11 or would we go to 8? So let's take a look. So you can see that it has 9 vertices and 11 edges. So we would basically get the minimum spanning tree being 8 edges, since E is equal to v minus 1, that is 8. So after sorting it, you get the following distance here. So the source, the weight, the distance, the destination, etc. So we're going to pick all the edges. So let's take an edge here. So we're going to pick edge 7 to 6. No cycle is formed. So we're going to include it in this case. So we have another edge. We're going to pick out 8 to 2. No cycle is formed. So we're going to take another one. So we have 6 to 5. No cycle. We consider that as well. So we're going to keep doing this process until all these edge cases are actually constructed. So we got another edge. We got another edge. You can see how each edge is adding. And since that we have edges is equal to 8, or that is v minus 1, we're going to stop there. Let's count back. So let's take a look at the time complexity of the Krushkals algorithm here. That's basically E log E O of E log V. The sorting of the edges take e log e time. So because we have each edge here. After sorting, we iterate through all the edges and find and apply the union algorithm. So the find and union operations can also take log v time in this case. Why? Because we're actually dividing the vertices by one, and by each step we're actually dividing them. So that's why we have the log v here. So the overall time complexity is basically, we have to add these up. So that's e log e plus e log v. That's the time complexity. So the value of e can be at most O of v squared, O of log v, or of log e at the same time. It depends on the tree, for example. Therefore, the overall complexity is e log e or e log v. So that is it, guys, and I hope to see you in the next video. We'll just be discussing about prims and the grading algorithms overall. See you soon.